So we're glad to have Emily Cliff from the University of Sydney, who will tell us about the Moduli principal bundles for a two group.
Okay, thank you for the introduction, for inviting me and giving me hosting privileges. Very exciting. Yeah, so this is joint work with these 5 people, Eric, Dan, Laura, Apurva, and Emma. And it started at the AMS Mathematical Research Community a year and a half ago, which was organized by Josh, among other people, and attended by Mache. So here's the plan for the talk. We're going to start with some motivation from physics. And I'm not a physicist, so it will be a little bit vague. And sections 2 and 3 will be about definition. So what is a two group and what is a principal bundle for a group? Beep, beep. And section 4 will be the construction of the Fried-Quinn line bundle, which is a line bundle that we'll see in the first section. Okay, so let's start with some field theory. So we start with the data of a compact group G and a 3 cocycle alpha. And we define from it a 3D TQFT. And in the case that G is a simple, simply connected group, this is called Chern-Simons theory. And in the special case that G is finite, this is Digraph-Witten theory. And that's the focus for us. And so let's remember vaguely what is the data of a 3D TQFT. So to each closed 2 manifold, to each closed surface, we're going to associate a vector space. I'm going to call Tx as a vector space, and we have the special condition that the empty set viewed as a 2 manifold should go to the unit vector space. And to each 3 manifold with boundaries, so this is a cobordism between one surface X in and another surface X out, we should associate a linear map. And in the case that the boundary is empty, both X in and X out are empty, then we get a map from C to itself, and so that's just a number. And then, of course, these should satisfy lots of compatibilities with composing. And maybe we want to extend our TQFT and say assign categories to 1 manifold and so on. But for today, a focus for us is where does this vector space come from? How do we define it? Okay, so let me start by saying how physicists define it, using the data of the group G and the cocycle alpha, and they define it using path integral constructions. So they associate to a manifold of dimension 2 or 3, or maybe smaller, a space, and this is the space of fields, which I'll denote by theta on this manifold. And they define, or say they define, a measure on this space. And they also have some kind of function, and this is called the action. And so then they define Tm, whether it's the linear map or the number or the vector space, they define it as a kind of integral over the fields with respect to this measure. And okay, I put e to the 2 pi I. So often they'll view their cocycle as valued in R mod Z. And so then to get a well-defined number, you need to take the exponent, but sometimes we do it in U1. Okay, and so here by this integral, we should interpret a bit generally. We should think of it more like we do in algebraic geometry, like a push forward, maybe to a point. And so the result could be a number or a vector space or something more complicated, depending on where this takes values. Okay. So this is what physicists would do, but the problem for mathematicians is that this measure is not necessarily going to exist. Okay. And so this formula is just a formal suggestive kind of thing, and this bothers mathematicians and it bothers physicists less. So physicists say, well, assume it exists, what properties does it have? And they're actually able to get quite far with that perspective. But it's still kind of an objection for mathematicians that this object is not defined.
Emily, sorry, a small question. Can you remind us for physicists, where does the alpha come in? It's not in the definition of space of fields, or is it?
Yeah, that's right. It's
G alpha space of fields, but is it?
It's not. It's probably not in here. Yeah, it's going to be in here.
In the action, okay.
Yeah, yeah.
I have another question. What's the relation, of this TM and the Chern-Simons functional?
So this, again, I'm not a physicist, so maybe someone else in the audience knows better than me. Yeah, but I think it's coming in here, this data. But let's see the special case where G is finite, because that's the only case that I kind of know what I'm talking about. Okay. So when G is finite, and again, we're going to focus on the case that X is a surface because we want to understand this vector space Tx, then the space of fields doesn't depend on alpha, as Valeria just pointed out. So the space of fields is the equivalence classes of flat principal G bundles on X. Okay. And I put flat in brackets here because G is finite, so every bundle is a flat bundle. But by analogy with the case where G has topology, we would want flat bundles, not principal G bundles. Okay, and so what is that? We look at functors from the groupoid given by the fundamental group of X to the groupoid given by the fundamental group of G, and we need to mod out by equivalence, which comes from conjugation by G. And so in this case, to give a functor is just to give a group homomorphism from pi1 into G, and this is a finitely generated group, and this is a finite group, and so there's finitely many choices. And so in this case, Cx is a finite set, and so this integral, whatever you define it, is some kind of finite sum. Okay, and so mathematically, we're much more equipped to handle this situation. And more precisely, T of X is going to be the space of sections, maybe with adjectives, of a certain G equivariant line bundle on, I'm going to call it curly L, on this category. And I should issue a warning, so I'm going to be a little bit sloppy throughout about the difference between the category and the stack. So at some stage, I've defined this as a functor category, and I should be taking a nerve and a geometric realization and so on, but I'm just going to kind of elide those steps. Okay, and so as we said, this is a finite set. So to give a line bundle on it is not interesting, but it's the G equivariant structure that's a bit more interesting here. Okay, and this L is called the Friedquin line bundle because it was introduced by Friedquin when they worked out the details of the theory for a finite group. And so I want to sketch how they construct L. And I'm going to use the equivalence between line bundles and
Sorry, let me ask maybe a naive question.
Yeah.
The line bundle is a complex line bundle or a holomorphic line bundle?
It's going to, I'm going to construct a U1 bundle.
I see.
Okay.
So do we have the holomorphic structure for this line bundle?
That is a good question. I think sometimes they put adjectives, so they want holomorphic sections here. But I can't remember in the finite group if we need that.
I see, thank you.
Okay, so here's how they construct L. So we're going to write down a U1 bundle instead of a line bundle. On the space corresponding to this functor category. So we need to give a functor from our category of functors into the groupoid point mark U1. Yeah, I guess just to clarify what I mean by this notation. So this is a groupoid with one object and morphisms U1. Okay, so I want to give this functor, but inside of this category, which is a bit complicated, we have
Can I ask a certain question? So maybe this is just a psychological question. What is the advantage of writing, functors point over pi 1, point over g, as opposed to hom pi 1 of x into g? So is that supposed to convey extra information that writing in terms of?
At the level of morphisms, and particularly when we get to two groups, at the level of two morphisms, the structure is different. So here I'm going to have functors between these categories with natural transformations between them. And if I just had group homomorphisms, then there wouldn't naturally be a higher structure.
Okay. All right, thank you.
Yeah. A good question. Okay, so inside of this category, we have we have its skeleton. So it's an equivalent skeletal subcategory. Okay, so I'm just going to choose representatives of each equivalence class. So I'm going to denote those by these. Here are the equivalence classes. And so I choose my representative row, and I just look at the automorphisms of row. So now I have exactly one object for each equivalence class and its automorphisms. Okay, and so it's enough to define the functor on this subcategory up to equivalence. And so then I just need to give functors from this groupoid to this groupoid. And that is now just a group homomorphism. And I'm going to call each one of them F sub row from the automorphisms of row into U1. And so this is what Fried-Quinn do in their paper. And so how do we do this? So let's recall that row is a map from pi 1 of x into G. And it determines something, let's call it P row over X. And the automorphisms of row are the elements of G, such that if you conjugate row by T, you don't change it. Okay. And so such a T gives an isomorphism of the total spaces, P rho. And so I use this data to define a principal G bundle on the product of X in the circle by taking the total space across the interval and gluing the two ends via T. Okay. So I've got my copy, and then I'm going to glue this end to this end using this isomorphism T. And so that gives me a principal G bundle on X cross S1, and that gives me a map. So here I'm really using the spaces, not the groups, from X cross S1 to the classifying space. And so finally, I can define F rho of this element T by pulling back alpha along this map. So now I have a cocycle on X cross S1, and I take the integral. And this gives me an element of U1. So then you need to work a little bit and see that this doesn't depend on choices of the class rho and so on. That gives a group homomorphism. But this is the way in which we obtain a line bundle L classified by now a two cocycle. Line bundles are classified by two cocycles, and this two cocycle we say is constructed from alpha via transgression. Okay. And this one can show has this G equivariant structure that we also need. Okay, so this is the construction that's been known for many years. And one goal of this talk is to provide a geometric or categorical construction of the total space of L, rather than just of these cocycles or of these maps. And the strategy that we use is category theory, which is another reason why everything has been phrased so far in terms of groupoids and functor categories. So starting from the data of this G and this alpha, we construct what's called a two group. So we'll define that shortly. It's going to be called curly G. So this is some kind of higher categorical version of a group. And we study the moduli space M of principal flat curly G bundles, whatever that is. And we observe that we get a G equivariant fibration, fiber bundle of some kind, from M to this functor category we've seen before, which I'm now going to start denoting by bun GX, and I'll put the flat here just for consistency. Okay. And we impose an equivalence relation on M such that the resulting quotient space is a line bundle, and we show that this is the total space of the Friedkin line bundle. So that's the idea.
Emily, can I ask a question?
Yes.
So in the strategy, is now G not finite anymore? I mean,
G is finite.
G, so you're going to stay with G finite. And in the construction that you sketched above, what was not geometric or not categorical? Because you said the motivation is to.
So I guess for me, as I think it depends, but if you're a topologist, you're quite happy that that giving these maps here, this is a line bundle. But for me, a line bundle is constructed from these maps. It's just a perspective thing. And so I start from something and I glue them together, and I'm gluing them using data like this. Whereas our construction is going to be kind of from the opposite. Rather than starting from pieces and gluing, we start from something big and collapse. I think you are now muted. I don't know if you're saying something.
I think for the connected, I mean, the group, it is natural to expect such a line bundle appear, because when we trace back to the Chern-Simons theory, we know that we can only take the Chern-Simons function over the function of our quotient z. So it is always taking functions on the S1. So I would say it's natural to expect such a bundle to be U1, but not other like model structures. But anyway, maybe just some nonsense.
Okay. Yeah. I think what we're doing is very special to the finite case, that we're able to be a lot more explicit when we have a finite set underlying everything.
So. Hi, Emily. Sorry, maybe one comment. So Free does construct this line bundle in the case of compact groups. And it's somehow as explicit, but it's more complicated.
Okay.
So, yeah, it's certainly more complicated.
Okay, cool. Yeah, for us, we only deal with finite groups. And then like the next step that we could even think about would be a torus. And then maybe we could think about.
Oh, by the way, I remember that there is also a construction by Quillen, and I think they proved that the construction from the gauge theory from the TQFT part will coincide with the line bundle of constructed by Quillen, and do we still have some categorical picture of this theorem?
I don't, I'm not familiar with it.
I see.
Yeah. Okay. So now we're kind of going to switch gears completely and forget about physics and even topology for a little while. And we're going to think about category theory. So here's the definition of a two group. This is a weak two group. So it's a monoidal groupoid. So we have all morphisms have inverses, and we have a tensor product structure. And we require that all objects and morphisms have tensor inverses. So for every object, there's another object that I can tensor it with. Let me be more precise here. Admit. So there is some other object that I can tensor it with such that I'll get the unit object. So the weakness here is that I am not specifying what that object is, and I'm not specifying structure maps related to it. If you do that, then you start having what's called a coherent two group. Okay. And in fact, I think all the examples that I will give you could be made into coherent two groups, but we don't need that structure for what I'm going to say. So let's start with some baby examples. So let's start with any group H.
Sorry,
and then
interrupt again. So just to help me digest. So a groupoid is right, is a category with a small set of objects and invertible morphisms. And you're saying that a two group, weak two group is the same, but in the category of tensor categories or something like this. No. No, that's not probably not what you said, right? So I'm digesting what I'm trying to digest what a monoidal groupoid is actually. So it's a category, but it's not only it's a monoidal category such that, which is also groupoid.
Yeah.
And then there's some compatibility between those two things. No, maybe.
I don't think at that stage you would need anything. And then so then the extra structure on top of that is that that we want the objects to have inverses under the tensor product.
I see. So for example, so an example, maybe that's what you want to say, but if I take a groupoid whose set of objects is naturally a group, is that a two group, or I need something more than that?
No, I think that's probably a coherent two group. You're probably going to need to specify the data that shows that those objects form a group, right? So for example, you might, no, I guess you don't for a weak two group. For a coherent two group, we would want data like that there's a map like this, for example. And so you would need to specify that. But for a weak two group, you don't. You just need to know that it exists. And I think from what you said, that should follow.
I see. Okay. So roughly, objects are a group and arrows are a group. I mean, very roughly said. I mean.
Yes. Yeah. And I think the example that you have in mind is a skeletal two group, but all of our examples will be skeletal. So.
Maybe.
Okay. So
maybe I don't know that's what I had in mind. I have no idea what I had, but okay. Anyway, thank you.
Okay, so starting from a group, there's two ways that we could try to define a two group, because as Valeria said, we could have the objects being this group, or we could have the morphisms. We could try to define the morphisms to be this group. So H bar is going to be the two group with the objects given by elements of the group and only identity morphisms. And we define H tensor G to be HG. So then we're supposed to define an associator that's part of the structure of a monoidal category. And so that should be a map from G tensor H tensor K, so the same thing with the brackets the other way. But of course, these are both just GHK. And the only map from GHK to itself is the identity. So this is a boring example, but it is an example. Now we can try to do the opposite thing, where we define point mod H to be the two group with one object and morphisms of that object. So that's Hom from point to point. This should be H, and the composition is given by the group structure of H. And now we want to define a tensor structure. And so that should be given by taking if we take the tensor product of the point with itself, it has to be the point. That's the only object. And we would like to say that, well, H tensor K should be a map from point tensor point to point tensor point. So it should be another element of H. And we'd like it to be HK. Okay. But now there's kind of an Ekman-Hilton argument to be done that shows the compatibility between composition and tensor products. And so for this to work out, H must be abelian. So to further to Valeria's intuition, we have a group of objects and we have an abelian group of morphisms.
And just to be sure, this is because like H here appears as the endomorphism. It's the endomorphisms of the identity object. That
Yeah.
all abelian or commutative anyway, I guess.
Right, because it's got two group structures that are compatible.
Cool, thank you.
Sure. Okay, so here's a more interesting example where we combine both of these ideas. And so this is back to our familiar data from the very beginning. We have a finite group and a 3 cocycle. And I haven't reminded you anything about 3 cocycles or told you. So in particular, it's a map that takes 3 elements of G and spits out an element of U1. So now we define our curly G as a category. It has objects, the elements of G, and it has morphisms So the Homs from G to H are, well, there's none if G is not equal to H. And there's a copy of U1 if G is equal to H. So this again, this is telling us that this is a skeletal category. And so I need to tell you how to compose. So if I have G, two maps from G to itself given by A and B, then the composition, okay. Now I should be careful about the order, but it doesn't matter because U1 is commutative. So I'm just gonna multiply these two elements. So that gives us our groupoid structure. And now we need to define the monoidal structure. And on objects, I'm going to do the same thing I did before. So G tensor H is GH. And on morphisms, it's also going to be similar. So if I had A tensor B, where A was a map from G to itself and B was a map from H to itself, then I should get a map by tensoring. And it's going to be a map in Hom GH, which is U1. And what is that element? I'm just going to multiply A and B. So we can get a little bit more in depth into the monoidal structure. So the unit object is going to be the identity element of G. And the structure maps that go with that are also going to be identities. So we're going to have a map 1 from G to 1 tensor G, or G tensor 1. Okay. And finally, I need to tell you the associator, which is going to move the brackets from left to right. And so again, this should be an element of Hom GHK to itself, which is U1. And what am I going to take for that element? I'm going to take alpha of GHK. So we somehow exactly have the data that takes 3 elements of G and spits out an element of U1. And let's remember that in a monoidal category, this associator should satisfy the pentagon axiom, which says that given 4 elements of the category, 4 objects of the category, we can tensor them starting at the left, or we can tensor them starting at the right. And we have 2 ways to identify these things using associators, and they should agree. So just to get used to these cocycles, let's remind ourselves what the 2 ways are. So one thing I can do is move the brackets so that K, instead of being grouped with GH, is grouped with L. So now I have GH tensor KL. Okay. And to do that, I use the associator GH, K, L. And now I want to move the H over. So here I have the associator GHKL. To go the other way, I'm first going to move the brackets inside of this triple here. So I'm going to get G tensor H tensor K. So this is alpha G H K. And then I'm going to move the brackets to move this HK over outside with the L. And so I'm going to use GHK, L. And then finally, I move the brackets inside the triple on the right. And so this is alpha HK L. And I should be a little bit more precise. So here, this is alpha HKL tensored with the identity on L. But that is just multiplication of this element of U1 times this element of U1. And so this is just alpha G HK. And same thing over here. Okay. And so what I get is that going around the diagram in a big loop like this should be 1. So if I write that out, so I have alpha HKL starting from here. alpha G, H, K, L, and alpha G, H, K. And then now I'm going the other way, so I'm going to invert these guys. So I have alpha G, H, K, L, alpha G, H, K, L, and this should be 1. But this guy here is exactly, if you're familiar with group cohomology, this is at exactly D alpha. So that's a 4 cocycle applied to G, H, K, and L. And so the fact that this 4 cocycle gives 1 is exactly the condition that alpha was a 3 cocycle. So somehow a 3 cocycle is exactly the data that we need to define.
And when we look at that, we found it very clear.
Was that a question or an accidental unmuting? Okay. Are there any questions? Okay. And it's also a fact that if you take 2 3 cocycles that are cohomologous, then you get equivalent 2 groups. Okay. So without loss of generality, we can replace alpha with a cocycle which is what's called normalized, which is that alpha of G1K is equal to 1 for all G and K. And in fact, once you assume that, it implies that alpha of G, H, K is equal to 1 when G or H or K is 1. Okay. So the theorem, which I think was written down first by Sin, she was a student of Grothendieck, and then maybe slightly more carefully in a published form. So it was in her thesis by Baez Lauda, much more recently, is that all essentially finite 2 groups arise basically in this way. And the basically means, well, U1 was a completely arbitrary choice. So I should replace U1 by any abelian group that has an action of G. So more precisely, any 2 group G, which has finitely many isomorphism classes of objects, is equivalent to a 2 group determined by the data of a finite group G, a G module. So in our case, we took the abelian group U1 with trivial action. And that's just to make the formulas simpler, basically. And then a normalized three cocycle alpha. And so you need to be a little bit more careful with the tensor product of morphisms when you have this G module structure. Okay, and so then we get a 2 group, and it fits into a short exact sequence using the examples that we saw earlier. So we have one, oh, not there, mapping to point mod A, so that's our morphisms. Like this. Okay. So our curly G is always can be viewed as some kind of extension of a finite group by point mod an abelian group. And it's a central extension exactly when A is a trivial G module. So in our case, it was a central extension. So going back to that U1 case, remember that central extensions of G by U1 are classified by H2, and analogously, central extensions of G by point mod U1 are classified by H3. And so you could imagine that we could generalize and have 3 groups and 4 groups and so on. And I don't know anything about them, but I think that they are needed if you want to do the extended field theory. So if you want to produce categories and 2 categories and so on. Okay, so that's the idea of a 2 group. It's this nice category with this extra structure. And now we want to say, what is a principal bundle for G? Okay, and at this stage, I was a little bit careful or not careful in the previous section because I ignored any topology. But there is a notion of a smooth 2 group where both the objects and the morphisms have smooth structures and so on. And so when we're talking about principal bundles, we probably want to keep this topology in mind. But again, we're dealing with flat bundles over a finite group. So the only topology we need to worry about is U1. Okay, so just as a warm up, because I did mention morphisms and equivalences of 2 groups, but I didn't say at all what they were. So suppose that we have finite 2 groups that are U1 extensions coming from finite groups G, H. So what does it mean to give a homomorphism of these 2 groups? Well, it should be a functor. It should be a homomorphism phi from curly G to curly H should be a weak monoidal functor, which means, in particular, I'm going to ignore morphisms for a little bit, but on objects, we have a map of the finite sets. And the monoidal structure is extra data. So for each G and H in the group G, we should have an isomorphism from phi applied to G, phi applied to H, to phi applied to GH. Okay, so this is the monoidal product in H, and this is the monoidal product in G. Okay. So this is the data that we need. And so this is an isomorphism in our category H, but H is skeletal. So we only have an isomorphism if they're actually equal. So actually, phi does need to be a group homomorphism. But we also have this extra data of M. Okay. So M is a map from G cross G to U1 that provides a collection of isomorphisms that demonstrate isomorphisms demonstrating this group homomorphism structure. So that's the general pattern that we're going to see, is that when we lift from the group setting to the 2 group setting, because we're working with skeletal 2 groups, we require all the usual data to satisfy all the usual equations, and we furthermore require a family of elements in U1 demonstrating that these equations hold. And then we probably require compatibility data when we go up a level.
Emily, can I ask a quick question?
Yes.
Why are you calling this a weak monoidal functor? So in my recollection, functor is weak monoidal if the monoidal structure, which you're denoting by M, need not be invertible, but you're actually postulating it's an isomorphism. So wouldn't that just be a monoidal?
Yeah, yeah. I guess what I'm saying is that this is not the identity.
Right. But that's right. That's yes.
Okay, so that's a
That's
terminology.
functor, right?
Sorry, can you say again how this map M demonstrates the homomorphism structure? I didn't get that.
Well, so in principle, like if these were just general categories and we had a monoidal functor between two monoidal categories, I would require an isomorphism between applying it to two objects and taking the tensor product and taking the tensor product and then applying the functor. And that's part of the structure of a monoidal functor.
Mm-hmm.
Now,
I guess I only wanted to ask about the last line. So M is a map into U1?
One, because we're working with G and H, and so HOMs from here to here are given by U1. This is particular to this situation.
Oh, I'm sorry. Of course. So they're the same object, but the isomorphism could be non-trivial.
Exactly.
Okay. Thank you.
Yeah. So we could always give a boring one where this was always one, but what's interesting in this situation is that it doesn't need to be one. Okay. And in fact, maybe we can't always have one because what we're going to do when we have G, H, and K is have some compatibility between these M's and the associator. And so not any random choices of M's are going to work. We'll see that in another example. Okay, so this is the general setting. We're always going to require this extra data of these isomorphisms. And so let's turn our attention to the case of a principal G bundle, which is determined by a group homomorphism from pi1 x into G. And so a flat principal G bundle is determined by a group homomorphism from pi1 x into curly G. And now we're viewing this as a boring two group. So this would have the overline in our very first example. And so the flat principal G bundle is determined by a pair, which I'm going to denote by rho and gamma, where rho is a homomorphism of the underlying groups, but gamma is a map from pi1 of x cross pi1 of x into U1, which we think of, so gamma AB is giving us an isomorphism from rho A, rho B to rho AB.
Oh, Emily, sorry, another question about your previous slide. So in
Yes.
that setting, the G action on U1 is still trivial? Or?
Yes, yeah.
Okay, thanks.
So, okay, but now I said this should satisfy a compatibility condition. So let's spell it out in this case. And it's saying, well, if I start with three elements, rho A times rho B times rho C, I'm going to end up at rho of A times B times C. And I can do that in two ways. And the compatibility condition is that either choice should give me the same thing. So for example, I can combine the rho A and the rho B using my gamma AB. So I get rho AB times rho C. And then I can combine these using gamma of A, B, C. And I'm going to write rho of A, B, C. And it's tempting here to put brackets. But this is ABC is an element of pi1, which is an ordinary group. So I don't need brackets. If I go the other way, so what I should do here is first move the brackets around. So I'm going to use the associator. So now I've got my rho B and my rho C next to each other, and I'm going to combine them using gamma. And then I'm going to combine again. So what has happened in this situation is that this morphism here, this 3 cocycle, is the same as going around this way. Or in other words, alpha of rho A, rho B, rho C is equal to gamma of A, B, gamma of A, B, C, gamma of A, B, C, and gamma of B, C. Okay, and so this is just some formula, but again, if you're familiar with group cohomology, what you see is that we have that the pullback of alpha along rho is equal to 1 over d gamma. So in other words, a flat G bundle is given by a pair rho and gamma, where gamma satisfies this condition here. And okay, but with this, the flat G bundles are going to form a category, in fact, a 2 category. So let's say, what is an isomorphism of flat G bundles? Okay, so these are not, sorry, this is just ordinary G bundles. So we have a map, an isomorphism from rho to rho prime, we saw was given by an element of T that conjugates one to the other. And so an isomorphism of flat G bundles is going to be given by a pair, one of which is the element T and the other of which shows that this is true. So it's a pair T and eta, where, so let's say that T eta is a map from rho gamma to rho gamma, rho prime, gamma prime. So T of rho A should be the same thing as rho prime of A times T for all A and pi 1 of X. And so for each A, I need a choice, eta A. So eta is a cochain from pi 1 of X to U1. And it should satisfy some compatibility condition that we could write down, but we won't for now. But that compatibility condition will involve what happens when you have T times rho A times rho B. And so you can move the T past twice, or you can multiply the AB together and move it past once. So it's going to be a compatibility condition involving alpha, gamma, and gamma prime.
Can I ask maybe a naive question?
Yes.
So could we, categorize the principal bundles which might be not flat?
Yes. Yeah.
How do we do that for not flat cases?
Right. So we should work to really do the topology properly. I should be viewing, instead of groupoids, I should work with Lie groupoids. So I'm going to have a pair G cross U1
Yes.
mapping to G. And I view this in the category of bibundles.
Yes.
Yeah. And so then we can form the notion of a G equivariant object in bibundles over a base that's locally trivial.
I see.
Yeah. But what we're going to, because we're working over a surface, I can phrase everything in terms of like check cocycle data on the universal cover.
Yes.
And so I can actually, working from that definition, spit out that actually I should have maps. Rho should be a map from X tilde, the universal cover, cross pi 1 of X into G.
Yes.
But then when we require it to be flat, we want it to be locally constant. So this part doesn't matter. If that makes sense.
I see.
Yeah.
I see.
That was a technical aside for experts, I guess. Okay. So in fact, flat principal G bundles form a 2 category. And the 2 morphisms are not that interesting. Again, kind of similar to in the definition of curly G, we only have 2 morphisms between 1 morphisms that are already equal, and they're exactly a copy of U1. So we get some 2 category, and I'm going to denote it by bund flat of curly G. And it has a natural map to ordinary G bundles, which was this category. And on the level of objects, it sends a pair rho gamma to rho, and it sends a pair T eta to T, and then it forgets about two morphisms. And so the next step, what am I doing for time? I'm almost out of time, so I will skip, I think, this definition. It admits a natural right G action such that pi is G equivariant. And so what do I mean by an action? I mean, let me just write this here. We want some kind of map F, which is going to be a functor from G to the automorphisms of this category. And so these are both viewed as monoidal two categories. So as you can maybe imagine, to write this down is lots of steps, lots of data, lots of compatibilities, but it's all pretty natural. And so there's a way of conjugating. We conjugate rho by an element of G, and we can also conjugate gamma in a certain sense. Okay, so we have a G equivariant family over the base. We want a G equivariant U1 family over the base. Okay, so we look at the fiber of this functor. Over rho, and I'm going to not take the homotopy fiber, although there's a model category argument that we can argue that it's fine to do this. So if I just take the ordinary pullback over an element rho, I get the pairs rho gamma such that D gamma is equal to 1 over rho star of alpha. And so if gamma and gamma prime are in the same fiber, then D gamma is equal to D gamma prime. And so they differ by a unique two co-cycle. So in other words, what I'm saying is that the fiber over rho is a Z2 torsor. So I'm going to take a quotient where I identify two pairs rho gamma and rho gamma prime if they differ by a co-boundary. And how do I do this? I do a kind of associated bundle construction at the level of categories. So I used to have fibers that were Z2, and now I'm going to have fibers that are H2 over my base. So this now has, so I didn't explain to you at all what we do with morphisms, but it is a thing. So it has fibers given by H2 of the group pi1 with coefficients in U1, and this is U1 for a surface. Okay, and so the theorem is that this U1 bundle agrees with the total space of the Friedquin, the U1 bundle associated to the Friedquin line bundle. And I'll just say a few words about the proof. And so the key lemma here is that in our equivalence relation, which I phrased as a condition on gamma and gamma prime differing by a co-boundary, that's exactly equivalent to these integrals being equal. And I'm going to define a map like this. To U1 mod U1. So here it's acting on itself. So what is this map? It sends a pair rho gamma to the element of U1 that we get by integrating gamma. So this is this object here. So this functor is somehow related to the construction that we just did. But on T eta, so that should be an element of U1, and I'm going to send it to this Fried-Quinn gadget. And this map, we factor this map through the quotient. And we can do that exactly because of this key lemma. So this is going to factor. And on the other hand, if I forget about the objects and just project onto the morphisms, then I'm only interested in this thing here. Okay? And we can see that this is independent of eta. So this factors through the ordinary group. And this part here was the Fried-Quinn functor. And so because of this, this is roughly how we see that this is the total space. Okay. So that is the conclusion for now.